Okay, here we go. 7.3 electric fields. So to start off with, what is an electric field? We were talking about gravitational fields in chapter 6. Now, electrical fields, it's the same idea. What we're talking about now, the electric force. So this is the electric force per unit of positive charge. So that's the electric force per unit of positive charge. Let's just say in a region. So if there's some region where there's electrical force on things, the electric field is talking about how much that is. And we have an equation for that. Well, our equation, we've got a few equations actually. To start off with, we can say that Fe is equal to Q times epsilon. And if we make F a vector and epsilon a vector, epsilon, that's a Greek character, it looks like an E, and that is our electric field. So here I'll put an electric field here, I'll just put this symbol epsilon. So if we have our electric field, we can multiply that by the charge to get how much force we have in the field. Okay, so we'll just say here, I'm going to say epsilon has units of newtons per coulomb. Okay, so that's our first equation, and the second equation that's going to be useful here is just by actually rearranging this, because from last lesson we have an equation for F, which was kq1 q2 over r squared. You might remember that one. So if we rearrange that one with our epsilon here, we can find that epsilon is equal to k q2 over r squared. kq2 over r squared. So that's epsilon. I'll just clean up that r squared there a bit. Okay, kq2 over r squared. And there we go. That's how we can find our electric field. It's a useful thing because then we can just use that electric field and multiply it by whatever charge is in the field to figure out the force. And the way we figure out these things, the way we measure these fields is by using what we call a test charge. So the idea is just we have some particle that has a single positive charge, and so our test charges are always a single positive charge. And the idea is that when we talk about our fields, we look at how this test charge would move in the field. So you can see on the right here we have a picture of Q2. Q2 is emitting an electrical field, and you can see that Q1 is our test charge in there, and we are measuring the force that it experiences, so we can talk about epsilon, the field strength there. Okay, great. So we've got a problem. Let's give it a try. The first one says 2-point charges are 45 centimeters apart. The charge on Q1 is 3.3 times 10 to the negative 9, and the charge on Q2 is negative 1 times 10 to the negative 8. So we've got a positive and a negative. We've got the picture over here. We want to calculate the net electrical field at point P, which is 27 centimeters from the positive charge, on the line connecting the charges. So we have R1 here was 27 centimeters. Good. And to do this, well, we can just use our equation. So the net electrical field. We're going to have an electrical field from both charges. So we're going to get the first electrical field, epsilon 1, and that's going to equal k q1 over r1 squared. All right, and so we just calculate our field. That's just the equation that we had above. So k, we use, sorry, 1 second. Remember we had our k value from the last lesson. So we're going to use that same number there, 8.99 times 10 to the 9. That's our k value. And we've got Q, in this case Q1 is 3.3 times 10 to the negative 9. And we divide that by R1 squared, which we said was 27. So 0.27 meters. We square that. And we get an epsilon 1 of 4.070 times 10 to the 2 newtons per coulomb right. And we say right because our Q1 is positive, and we're always talking about what effect would it have on a positive charge. So in this case, we would be pushing it right. Okay, and we do the same thing for epsilon 2. Epsilon 2 is equal to k Q2 over R2 squared. Good. Now we're going to have to figure out what R2 is. It said it was 45 centimeters apart total. So that was 45 total. 45 minus 27. So we're left with a distance of 0.18 or 18 centimeters here. Okay. So now we can go back down to our equation. We've got 8.99 times 10 to the 9. We've got Q2, which was negative 1.00 times 10 to the negative 8. Divide this all by our R2 squared, which was 0.18 squared. That gives us a value of 2.775 times 10 to the 3 newtons per coulomb. And let's see, we've got a negative charge, so it's going to be pulling a positive one. So again, this is going to be towards the right. And I haven't really left me any space for doing the last step here. We want to get the net. So let's just see. Epsilon net is equal to epsilon 1 plus epsilon 2. You can see they're in the same direction, so I can do those two numbers added together, and it gives me 3.2 times 10 to the 3. And it's newtons per coulomb right. Okay, and this is, this is our final answer, so that's important. Sorry, it's kind of squeezed in there. All right, part 2 here, it says a new charge of 2 times 10 to the negative 12 coulombs is placed at P. Now we want to determine the electric force on this new charge. Okay, this is why we bother calculating our electric fields, is that now we know how much that's going to experience. We have an equation. We just say our net electrical force, Fe net, is going to equal Q times epsilon net. We have epsilon net, and we have Q. So we can just plug in those numbers. We have 2.0 times 10 to the negative 12, and we have our epsilon net was 3. I have a few extra digits from above. 3.182 times 10 to the 3. This gives us a net force of 6.4 times 10 to the negative 9 newtons. And our direction, it's the same direction as our field was, so it was to the right. And that's all we need. Now notice that if it had been a negative charge, an electron, we would have gotten negative 6.4, that sort of thing, right? So it would have been a negative number, so in fact it would have been a force to the left in the end. So that's just how it works with the positive and negative. Okay, good. So let's try another problem here. 2 point charges are arranged as shown on the right there. Q1 is 4 times 10 to the negative 6, Q2 is negative 2 times 10 to the negative 6, and R is 3 centimeters. We want to calculate the magnitude of the electrical field at the origin. Alrighty, well, we got to calculate our two electrical fields. So I'm going to do the E1 from the first guy here, and it's going to be K Q1 over R squared. And so we can just plug in our numbers. 8.99 times 10 to the 9. Q1 is 4.0 times 10 to the negative 6, and our R was 0.03. Square that. This gives us an epsilon here of 3.996 times 10 to the 7 newtons per coulomb. And this one was, so from Q1 it's going down. All right, we'll do the same thing for epsilon 2. K Q2 over R squared, 8.99 times 10 to the 9. Q2 was negative 2 times 10 to the 6, 10 to the negative 6, sorry, divided by the same radius squared, and that gives us 1.998 times 10 to the 7 newtons per coulomb. And this one, so let's see. Our Q1, it was positive, so it was exerting a downwards force. Q2 is negative, so it's going to pull it to the right. So these questions do involve just thinking about directions there. Okay, so we have our epsilon 1, epsilon 2, so now I could draw a little picture. I have down and right. Down, right. This one's This one's about 4 and about 2. I'm just going to put those numbers in there. I'll use the real numbers in the calculation. And this is going to be our total epsilon. So we're going to need to get our angle and our magnitude. So we can say epsilon is equal to the square root of, we've got 3.996 times 10 to the 7 squared plus 1.998 times 10 to the 7 squared. All of that gives us an epsilon value of 4.5 times 10 to the 7 newtons per coulomb. And we need to get our, we don't need to get our angle because we just need the magnitude from the question. So there we go. That is our magnitude. On the next page here, we have electric field lines. So we've been talking about electric fields. Now, when we want to actually visualize them, we visualize that by drawing lines. We draw these little lines going around the objects. And so, first off, we'll say electric field lines, they are continuous lines of force that show the direction of electric force in a field. So we have our field. The field lines show us where the force is going and what direction they're going. And now one thing is, just like other fields, the denser the lines are, the closer together they are, the stronger the field is. So that's how those work. Okay. Direction. So the direction is always going to be the direction a positive charge moves. Okay, so if you stick a negative charge in there, it'll just move opposite the direction of your field lines. All right, you'll notice that we have the inverse square law in our electric fields as well, because we're dividing by r squared. And in fact, if we looked at that equation, I'm just going to pop back to the last page for a second. This equation, epsilon, is Q2 over r squared. Looks a lot like G. Looks like a lot like our gravitational field strength, where G was equal to big G times m2 over r squared. So they're a very similar situation. And remember, gravity had our inverse square law. So does this one, the electric field. So again, we have our inverse square law, which we can say that Well, I'll just leave that blank. I just wanted to point out that there is an inverse square law. There's a picture of that on the right here that you can see that we'll say that the field strength is spread across the area of a sphere. So the idea is that as you get further away from something, that sphere is getting larger, which means that if we're dividing the energy over that surface of the sphere, it becomes smaller, because the area of that sphere gets larger and larger as you get further from the object. Okay, so that's our idea of electric field lines. Couple more small topics here. Electric dipoles. So an electric dipole is where you have a positive charge and a negative charge, and they're sort of connected, or they're put together. So you can see a picture to the right there. We have negative Q and positive Q. And the idea with an electric dipole, well, we'll just say here, this is a pair of equal and opposite electric charges. And that's basically it. We'll say separated by a small distance. Good. So that's our dipole. And what happens with the field lines is you'll see that they end up looking a lot like a magnet does. If you remember from grade 11, they look like a magnet. So the field lines, they point from the positive charge to the negative charge. They look like a magnet. You'll notice they are parallel at the midway point between the charges. So if you look at this center line here, what I'm saying is that the field lines are parallel. They're all going exactly horizontal here at that halfway point, which is interesting, and we're going to see how that relates just at the end of the lesson here to another idea, these uniform fields. All right, so that's an electric dipole. There's two other interesting things we can look at, sort of the field lines for what happens here. And so here we're just looking at a couple interesting patterns for magnetic or electric fields. So you can see when we have two positive charges, well, this is this picture here, two positive charges, and the other one is this picture here. So we have two positive charges, and you can see that they cause each other to sort of point away from each other. You see that we have this center line where nothing goes across, right? And so it creates this sort of center line between the two fields. So we have a center line with zero electric field. And the other interesting thing about when we have two positive charges very close to each other, so you can see that they're repelling each other, but if you get far enough away, you know, they're all going out in a circle. It looks the same as a single positive charge would look. And so when you have two positive charges, you bring them together, if you zoom out far enough, it just looks like one single positive charge with twice the magnitude, which is how it works. We can group together charges, and if we zoom out far enough, it looks like they're just a single one. And it's only when you get into the nitty-gritty close up that it looks different. All right, the other thing we have here is like a dipole, but we have 2Q and negative Q. And you can see that it creates a bit of a shape like a dipole, but it's a bit imbalanced. And the main thing is that the positive 2Q has twice the lines as the negative Q. Has twice the field lines coming out of it because it has twice the charge. Remember, the field lines, the number of field lines corresponds with the amount of charge. The more field lines, the denser they are, the more charge there is, and the more electric field. All right, last little piece here, uniform electric fields. So you can see that a uniform electric field is where we have an electric field all going in the same direction. They're all parallel. So you can see that we have all these lines here. They're all going in a parallel direction. And that is, I guess what we can say about that is that the field lines are parallel, and it is created by placing two large plates near each other, with opposite charges. And these uniform fields can be very useful. They're very interesting. It's almost just like we have some sort of tidal force, something that's pushing any particles in that area in that direction. So you will have some problems that deal with those, and in the next lessons we'll deal more with uniform electric fields. That's the lesson. I hope you enjoy it.